Hello, this is Bob McFetrich with Beckwith Electric. I'd like to thank you for downloading our M-6200 training series. This particular session we're going to talk about predictive maintenance, and a few of the features we'll be talking about are our motor profile, our run-through neutral, and our different operation counter limits that we can look at. And again, we're focusing in on the M-6200A single-phase regulator control. So our motor current profile looks and monitors the actual current going through the motor of the regulator. So this is not load current we're talking about, but we're talking about the current that's actually going through to drive the regulator to make a tap. And when we're looking at the motor current, there are three different things we're looking at. Number one is how long is the motor current present during a tap. Number two, what is the average current being drawn by the motor during a tap? And number three, what is its peak RMS current draw during a tap? Once we calculate what the average is for a particular regulator, we can then set alarm limits above those averages to alarm the user that it's time to perform maintenance on the regulator. And once we learn what a normal value is for the regulator, that value can be reinitialized and restarted into a new learning mode again if we were to move the panel to a new regulator, or if we were to have just performed maintenance on the existing regulator and we want to start over. Now, the way we do this is what's called learning mode. And in learning mode, when a panel powers up for the first time, it'll enter learning mode, and it'll stay in learning mode until it sees 20 operations. And an operation can be a raise or a lower, and an operation can be one that's caused either an automatic, manual, or remote. So it doesn't matter how the regulator is tapping, but the first 20 times it taps, we're going to make our measurements and then have an average. Now, you can put the panel into learning mode by resetting it here, and you can verify whether it's still in training mode by looking at this screen. So if we go to File, Motor Current Profile, what we're seeing on this screen is it's telling us it's still in training mode. Right now, we don't have anything because it's not currently tapping. But this is the current average. So we've seen a few taps, but we must not have gotten to 20 yet because we do have numbers in here. And we can see by the duration that this is probably on a Cooper quick drive at 16.7 milliseconds. And again, we can reset it and start over if we need to. Now, once we have the values, we can then go to this screen under Configuration, and if we scroll down to the bottom, we can see that we have some motor current settings, and it allows us to enter in percentages above the normal value calculated for both the peak RMS, the average RMS current, and then the average duration. And these percentages are done in percentages of what the normal value is once that value is determined. Now, one of the things we can look at with motor current is we can also look at the actual waveform. We have a separate program that comes with Tap Talk called Tap Plot. So if you go under Utility and Tap Talk, the very bottom one will be a link to open up Tap Plot. From Tap Plot, I can open up oscillographies, and we're going to show you in another session on advanced features how to generate oscillographies. But once you capture one and retrieve it, one of the things we can look at is the motor current. And so here we can look, for instance, at when the raise contact got up, when the motor current started, when the raise contact went away, and when the motor current went away. And so you can see, if we look at the marks here, that this particular trace started at 11:39:22.6 and ended at 11:39:26.2. So this is probably a Siemens or a Howard regulator because we're looking at approximately 4 seconds for the tap. So you can see we have a large amount of oscillography we can look at, and that normally with a fault you're looking at cycles. Here we're looking at seconds worth of data. And here we can show a Cooper quick drive with multiple taps. So you can see that the lower contact is up for the duration, and you can see that we take a tap, wait, take a tap, wait, take a tap, and so this is driving multiple bands. And if we were to look at the timing, for instance, the timing between these two taps is 0159, 408 milliseconds to 660, so it's approximately 400 milliseconds per change. And here is a case where we're actually looking at motor current, and this is on a Cooper also, but notice we have a lot of harmonics on the voltage and the current, and you can actually see that the harmonics are also affecting the motor current. So the motor of this regulator will have a reduced life due to the amount of harmonics that are on the motor and on the actual load of this particular regulator. And finally, we were talking about the different values, one being peak and one being average. So you can see on this particular regulator that the peak current was about 700 milliamps, but once it got running, it's about 325 milliamps. So you can see that when a motor first starts up, it requires more current to get the torque going, but once it gets to rated speed, it levels off. So for this particular regulator, it's requiring about 713 milliamps of load current to get started, but once it gets moving, it's down to around 325 milliamps of motor current to keep the motor running. And from a DMP standpoint, there are several things we can look at. From a digital input alarm standpoint, we can see whether the current has been exceeded, either the RMS or the peak or the duration. So have any of these been exceeded? And under analog outputs or analog inputs, we can see the duration. So these are the current values and these are the average that have been calculated. So on the last tap, what was the value and what is the average value that's being used to compare to see whether it's out of range or not. And again, it's on all three quantities: the average, current, the peak, and the duration of time. So that's a brief run through on the motor current. Our next topic is going to be run through neutral. So single phase regulators have 8 physical taps in each direction, and you can go, they really only have 8 physical taps. So to get from -16 to +16, it's a combination of, if you're between 2 taps, that creates another tap, and that gets you 16 total. But then there's also a reversing switch that switches the polarity. So on the raise side, it's adding, and on the lower side, it's subtracting from the incoming voltage. And that's how we get to 16 raise versus 16 lower, is there's really only 8 taps, but crossing between each tap gives us another that gets us up to 16. And then the reversing switch is actually what's going to change the polarity for our raise versus our lower. And that reversing switch can get gummed up if it's not operated periodically. So in the old days, operators used to go out on site, look at the drag hands, and if they saw that a regulator hadn't gone through neutral in a while, they might put it in manual and run it through neutral just to exercise that reversing switch. And to exercise the switch, you have to go one more tap. So for instance, if I was on 2 raise, I would have to go to 1 lower to get that reversing switch to actually move and exercise. So the run through neutral is an attempt to do the same thing. It allows the user to periodically have the regulator go into manual on its own under certain conditions and then run through neutral and then go back into automatic. So first of all, we have to enable the feature, and we're under the configuration screen of TapTalk. Once the feature is enabled, the next setting is how many taps do we have to be within neutral. So obviously, if we're at -12, we probably don't want to run all the way up to neutral just to exercise the reversing switch, because that may cause very high voltages close to the source. So we have to be within a certain number of allowable taps before we can even start. The next thing is, how many operations can we go without going through neutral before we even start to try this? So in this case, if we go 1,000 taps consecutively without going through neutral, then we're going to enable the feature, and the next time we get within 4 taps of neutral and the maximum load current is below this setting, we will go ahead and allow it to tap. So again, we may not want to run this feature under high load conditions. So what we're saying is, if I go X number of taps without going through neutral, the next time I get within X number of taps of neutral and the load current is below this setting, go ahead and allow the panel to go into manual, allow it to tap to neutral and then 1 additional tap, and then return it back into automatic and let it regulate on its own. Now, as an additional alarm down here, once we have exceeded this and we start wanting to tap, this one says if I go 20 taps and the conditions are not met yet, alarm me. So once I start looking to run through neutral and I exceed the number of taps because I can't go either due to I'm too far out on the tap or the load current, then I'll generate an alarm saying that I want to run through neutral, but the conditions have not been met to allow me to do that. So those are the settings for the run through neutral feature. And we have a alarm down here, return failed to operate. And again, this alarm is triggered off of I've need to run to neutral. I've exceeded the number of operations since the regulators run to neutral, but I have not been able to enter that mode because either I'm not within the predetermined number of taps or my load current is above the predetermined maximum setting. We also have our analog outputs, which are settings that we saw before: the number of operations that you're going to allow, the number of taps without going through neutral before you alarm, the maximum load current, the number it's got to go, the maximum number of taps, and whether the feature is enabled or disabled. So all those are settings that can be set via DMP. So finally, our last topic is the operations counter. And that can also be used for predictive maintenance, and we have several different operation counters. So if we look here under the tap settings screen, we have a backwards counting operations counter. So basically what this says is, after I've seen so many operations generate an alarm to skate, it's time to do maintenance. So if I were to set this at 10,000, for instance, it would start counting down, and when it got to 0, it would be time to do maintenance. And the neutral counter is in the same manner, only here it's just counting the number of times through neutral. So after I've gone through neutral so many times, I may want to do maintenance. Operation counters that can come back as analog inputs under DNP would be our resettable operations counter, our neutral counter, and then we also have a counter that counts the number of lowers and the number of raises that have been attempted.